Hi, my name is Bill Kinney. This is video number 17 of a series about complex arithmetic methods and geometric interpretations. And I realize I probably should have been putting some other kinds of subtitles in these videos from the start. I'll start now here with video 17. The subtitle of this one, or even subtitle, is Applications of de Moivre's Formula and Euler's Formulas. We have been looking at de Moivre's and Euler's formulas in recent videos. Down here is Euler's formula. E to the I theta is cos theta plus I sine theta. De Moivre's formula is right here. Focus on the outside things in that string of equalities there. We did look at applications of de Moivre's formulas in recent videos, mostly to deriving trigonometric identities in kind of neat ways. This was one identity and here was another. Though these identities, while they are true, it's hard to imagine much use for them. You're taking, for example, here a relatively simple expression for a cosine wave of period 2 pi over 3 and writing it as a more complicated expression involving cosine and sine waves and products and a subtraction, with each trig function there having a period of 2 pi. True, but maybe not very useful. In this video, I want to go down to these expressions that we have from the last video in terms of for cosine of theta and sine theta, and show that you really can do something fairly useful in real life with these things. There is an application just like what I'm about to do in the book that I'm going through, the book Fundamentals of Complex Analysis by E.B. Saff and A.D. Snyder. A very similar example, I'm going to do a slightly simpler example. It is going to be still an application to evaluating integrals. And the integral we're going to try to evaluate here is going to be an indefinite integral of cos cubed theta d theta. Alright, that's going to be the integral that we're going to evaluate. And how are we going to evaluate it? We're going to use this formula up here. Counterintuitively, we're going to go into the complex plane, use complex functions to evaluate our integral. We're going to replace cosine theta with this complex expression here, e to the I theta plus e to the negative I theta over 2. One thing, you might wonder why this is going to be helpful. Well, it is not the only way to do it, but it is fairly helpful. It's fairly quick once you get pretty good at this. For one thing, you can bring the 2 cubed out as a 1/8 and then just integrate the cube of this thing. And you can cube that with the binomial theorem. We've got a cube there. That means we're going to need to take the first thing and cube it, which, if you think about it and use properties of exponents, is just going to give you e to the 3i theta. Then we're going to add 3 times the first term squared times the second term. And if you think about that, when you square this, you're going to get e to the 2i theta. And when you multiply that by this one, you're just going to get e to the I theta. If you didn't catch that, I'll say it again. In the second term of the expansion from the binomial theorem, focused on the numerator of this fraction, when you square the first term, you're going to get e to the 2i theta, but when you multiply it by e to the negative I theta, it's going to simplify to just e to the I theta when you combine those exponents. We still have the 3 here from the binomial theorem. The next term is also going to involve a 3, and it's going to involve one of these and 2 of these. So you're going to get e to the I theta times e to the negative 2i theta, which will simplify to e to the negative I theta. Finally, the last term cubed, e to the negative I theta cubed, is going to be e to the negative 3i theta. Now, what do we do from here? We could use Euler's formula. In fact, we will use Euler's formula to expand each of these things out in terms of cosines and sines. And you could certainly do that and show it all by hand, but I want you to realize that you can actually do it in your head more quickly once you get some practice. Think about this. You've got e to the 3i theta here and e to the negative 3i theta here. From Euler's formula, you're going to get a cosine of 3 theta and a cosine of negative 3 theta. Since cosine is an even function, those are really the same thing. Cosine 3 theta equals cosine negative 3 theta. In other words, they're both cosine 3 theta. You get 2 of them. So you're going to get a 2 cosine 3 theta. On the other hand, with the sine terms involving these 3 thetas, you're going to have an I sine 3 theta and an I sine negative 3 theta. Sine is an odd function, so those actually cancel and go away completely. You don't have any more sines of 3 thetas. Catch that? Think about it. Maybe write it out if you are unsure. The I sine 3 theta and the I sine of negative 3 theta. The negative can be factored out in front, and ultimately you can cancel those terms, and there's no sine of 3 theta. Now focus on the inside terms. From this one, you're going to get a 3 cosine theta, and here you'll get a 3 cosine negative theta. Again, cosine is an even function. That's the same as 3 cosine theta. Altogether giving you 6 cosine theta. If that went too fast, write it out, think about it. With the sine terms, they once again cancel. You'll have a 3 sine theta and a 3 sine negative theta. The negative sign can be factored out. There's i's in there as well, but ultimately you get cancellation of the sine terms. The imaginary parts go away. You do get a real integral here, which stands to reason since you started with a real integral. That's real. This is real. So that was a little tricky, and you probably want to maybe rewatch it and make sure you write it out and see how the cancellations happen and the combinations. We ultimately get a simpler integral to do, and let me go ahead and cancel the 1/8 to leave a 1/4 and have a cos 3 theta in here plus 3 cos theta. This is an easier integral to do. The integral of cosine theta is sine theta plus c. We have a cosine 3 theta. You could think of this in terms of the substitution. Let u equal 3 theta. Then du would be 3d theta. And ultimately, you should see, and you should try this on your own again, that you'll get a 1/3 when you integrate that out. With the 1/4, that'll combine to a 1/12 sine 3 theta. And with this one, the cosine theta is just a plain cosine theta, so that you don't have to think about substitution there. You're just going to get a 3/4 sine theta plus c. We've done the integral. This does work. This is the answer for this integral here. We could try checking it. See if it seems reasonable. Compare the plots of cosine cubed, which I have to type in like this, and this antiderivative of it. I'm using Mathematica's plotting command, I guess, for the first time in this series of videos. Plot is the basic command being used here. I'm putting 2 functions inside curly braces separated by a comma. I'm trying to see if one function is the derivative of the other. It might be nice to color code them so that we can tell which one is which. Let's make the original function we were integrating red, and the new function, the antiderivative, let's make that blue. So the derivative of the blue should be the red. Does that look right? Does the derivative of the blue look like it's the red? Well, the slope of the blue is positive, the value of the red is positive. Slope of the blue is 0 right there. Looks like at pi over 2, the value of the red is 0. Slope of the blue becomes negative, the value of the red becomes negative. Yes, It does look like the derivative of the blue is the red. In other words, the blue is the antiderivative of the red, or an antiderivative. It does look like this is probably right. We're at about the 10-minute mark here, so I think I'll stop this video and maybe we'll check this in the next video.